Good morning, everyone, and welcome to this class. This is Thermodynamics or Heat lecture number 11. In the previous lectures, we have dealt with calorimetry and thermal expansion, and it is done. I have sent you the exercise, I have sent you the sheets. So I hope that you are solving it and you solve each and every question of both the sheets. Now remember, I have told you before as well. Again, I repeat you, if you just do the questions that are there in the sheets religiously, each and every question, you have done good enough to clear any exams. Just to cite an example, I'm again telling you just to give you that confidence that in the previous year, I mean September, October, last year we had this crash course, and in that crash course, I had just taken selective topics. You might be knowing about it. I had taken heat also in those selective topics. We had covered some selective questions, some selective theory, and you will not believe that out of those questions, just in thermodynamics, I'm telling you, three questions, three and a half, in fact, came in the JEE Advanced ka paper. One question, which I'll again cover in this class, it came exactly the way I had done it. The only difference was I had done the question as V naught by 4, and in JEE Advanced, the question came as V naught by 2. That was the only difference between the question that I did in the class with the question that came in JEE Advanced. Anyways, I hardly get to see JEE Mains ka paper because there are too many papers, too many shifts. But I'm pretty damn sure whatever paper of JEE Mains I have seen in the previous years, they don't come out of what I have told you. And some questions will come ditto as well. So the bottom line is just do the questions that are sent to you and just give your papers correctly, and I'm sure we have done good enough to clear JEE Main or JEE Advanced for that matter. Okay, on that note, let us start today's class. And since we are done with calorimetry, I think the logical continuation for this topic is that we cover the next one, and the next one is heat transfer or transfer of heat. Since in calorimetry, where we are dealing with how much heat is going from the hotter body to the colder body, heat gained is equal to heat loss. This much amount of heat has gone, this much amount of heat has come. Now let us look at the process by which this heat actually gets transferred from one place to the other place. And I hope all of you know that there are basically three modes of heat transfer. The first one is, and the major of these is conduction. Conduction is normally covered very nicely in all the classes. You must be having a fair idea about conduction. Convection, this is not in JEE course, but that doesn't mean that nothing can come from this. I'll give you a fair idea about this as well. So if any question comes, see, there's nothing that's course for JEE. I'm talking about JEE Advanced. When I say JEE, I mean JEE Advanced. So there is nothing like course for JEE. There is a topic known as Coriolis force. Coriolis force. That is definitely not in JEE. But I think 4 years back, they gave a question on Coriolis when we had done Coriolis force in that class at that point in time. The students were able to do that question. Now, since it was out of course, what they had done, they had given a big paragraph. And in that big paragraph, they explained what is Coriolis. They gave the formula of Coriolis. And then they gave a question based on that. So now it does not remain out of course. It just becomes a part of your course. So nothing is out of JEE Advanced course. They can give you a question in paragraph form with 2 or 3 sub questions, and then you can score 4 or 6 or 8 marks or 9 marks depending on how much the question is marked. So they can give a small paragraph on convection, and they can ask you any question on convection as well. So we cannot rule it out. The third one is obviously radiation. Now this topic, radiation, may not be covered nicely in all the classes that you might have encountered, but we will be giving equal importance to conduction and radiation. Convection, we will just go through, and I'll just give you a formula. Again, it is not in your course, but I'll give you that so that if it comes, you have previous knowledge and you don't have to spend a lot of time in reading the entire paragraph. You can just mark the options and you can move ahead. First thing is definitely conduction. Now, since you cannot talk on the mic, I can't ask you whether you know what is conduction or not. But still, it's my job to ask you, what do you mean by conduction? Now, if I just give you a brief introduction about conduction, what do you mean by conduction? Conduction is a mode of heat transfer. We all know this. Now, if we talk about in which type of bodies conduction is the primary means of heat transfer. Remember, in all materials, in all bodies, heat can be transferred by conduction or convection or radiation. All the three modes are possible, but because of the properties of these bodies, maybe one, maybe two of these processes are easier to happen. For example, conduction is the mode of heat process that takes place basically in solids, but that does not mean that liquids and gases do not conduct. Yes, liquids and gases also conduct, but their conduction is very, 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 very slow. And it's so slow that you can neglect that conduction happens in these bodies. So basically, this happens in solids. What about convection? Any idea? Where does convection happen? Convection is the mode of heat transfer that takes place basically in fluids. When I say fluids, I mean anything that can flow. Now, this convection per se cannot happen in solid because this involves the actual transfer of atoms or the carriers actually get transferred. So it may not be so prominent in solids because hardly any atom will pass from one end to the other end. But anyways, convection, fluids. What about radiation? Any idea about radiation? We'll be discussing it in detail. What about radiation? Now, radiation is a mode of heat transfer which can take place in any body. This body is radiating. Any body that you see around you is radiating. So it can happen in all of the bodies that you see. That does not mean that the other two does not happen in all bodies. They do happen, but it's very slow and it's very less, and you can actually neglect whether it is happening or not. For example, conduction is very, very slow process in in liquids. So heat will not get transferred by conduction. It will probably use convection, which is better, faster, or definitely radiation. Now you will say radiation, how it happens in liquids? Well, you have a cup of hot tea, you keep it. After some time, that does not remain hot anymore. It has lost heat. It has given out heat. Not actually purely by convection, but the major part of it has gone out by the process of radiation. Everything, everything, everything radiates. These are the three modes of heat transfer, and we will be discussing them in quite detail. So once you are done with this, I hope that you will be able to solve majority of the questions that ever come. Now let us get into the heading of the first one. And the first one is definitely conduction. Now the question comes, what do you mean by conduction? We already know that conduction is the mode of heat transfer that takes place in basically solids. Now the question would arise, why it happens only in solid, and how does heat get transferred from one end to the other end? Anyone has any idea about this? How does heat get transferred from one end to the other end in the process of conduction? Let us assume that this is a rod AB. This is a rod AB. Now let us assume that I am holding this metal rod, because metals are very good conductors. I am holding this metal rod from one end, let us say from end A, This is the metal rod. I'm holding it from the end A. The end B, if I put this end B close to fire or in boiling water or ice, just touch it with ice, what will happen after some time? It will take some time to happen. What will happen after some time? Even though only this point or this part is getting touched with the higher temperature or lower temperature, very soon, slowly maybe, you will find that on the other end where you are holding this rod, you will start to feel that the rod is getting hotter or the rod is getting colder as time progresses. One end is kept at a higher temperature. Let us say the temperature of this end is T1 and the temperature of this end is T2. And we are trying to keep T1 and T2 constant. This higher temperature on point B, heat is going to get transferred from point B to point A. Do we understand this? Yes or no? The more that which this heat gets transferred, since T2 is at a higher temperature compared to T1, heat always flows from higher temperature to lower temperature. We have already seen that heat will start to flow from end B towards end A, and this process is known as conduction. So basically, what do I know about conduction? This is the mode of heat transfer that takes place in solids, basically. That does not mean that liquids and gases do not have conduction. Now, why it happens in solids? Now, what is the procedure? What is the phenomena by which conduction takes place? So inside this solid body, we have molecules, atoms, where they are very closely packed with each other. Now, what is happening on end B? When end B is at a higher temperature, the atoms or molecules, since they are at higher temperature, they have higher energy. So they are vibrating or oscillating with higher energies. The energy is more compared to the atoms on the other side, and A, they are also vibrating, they are also oscillating, they are also moving, but with lower energies. So at the end B, higher energy, at end A, lower energy. So what will happen when they are vibrating, oscillating? They are going to collide with their neighboring atoms, and they will transfer a part of their energy to the neighboring atoms. Then those neighboring atoms will now start to vibrate at high energy. They will transfer the energy to the neighboring atoms, and then the neighboring atoms, and then the neighboring atoms. And in this way, by this collision between the atoms, the vibrating atoms, the collision between the atoms, heat energy get transferred from the hotter end to the colder end. Remember, there is no actual transfer of atoms taking place. There might be one or two atoms which might go from this end to this end, but as such, there is no actual transfer of atoms from the hotter end to the colder end. They are just vibrating with high energies, and that energy, by means of collisions, is getting transferred to the other end, and that is how heat energy is transferred from the hotter end to the colder end. This is getting transferred because of the collision of atoms or molecules, whatever you call them. Collision of atoms or molecules. There is no actual transfer of the atoms. There is no actual transfer of atoms, but in one of these processes, the atoms or the molecules are actually getting transferred, and this mode is convection. In convection, atoms and molecules do actually move, and that is how heat is transferred. Now, since it is because of the collision of these atoms or molecules, now if the atom or molecules are very far apart from each other, the collision will happen, but the collision will be very less, and the energy transferred would be very, very slow. And therefore, this mode of heat transfer is not very prominent in liquids and very, very less in gases, because in gases, atoms are very, very far apart from each other compared to solids and liquids. And therefore, conduction happens in solids primarily. Do we understand this? Have you understood this, that this is how it happens, and that is why it happens only in solids? liquids and gases, it happens, but it is very, very, very slow. So these are the 3 points that we must remember about conduction always. Now, when we are talking about conduction, the process of conduction may be very complicated, but we are going to understand it in very simpler terms. See, we are not studying physics in great detail. We are not doing a PhD in conduction. We'll be trying to understand a very easy form of conduction where everything is sort of fixed. Everything is steady. Everything is a constant. Everything does not change. Now, the mode of transfer conduction, we are going to study a very, very simpler version of that. And that simpler version is known as the steady state. Steady state of heat transfer. Steady state in conduction. Steady state. Have you heard this term, steady state? Any idea about this term, steady state? Either the answer is yes or the answer is no. Okay, then tell me, what do you mean by this steady state? If you've heard that term, that is very good. My job becomes simpler. Now tell me, what is this steady state? What do you mean by this steady state? What do you mean by this steady state? So, what I have done here, I have taken a solid body, and whatever is here is insulation. Now, why I have insulated this? So that no heat is getting lost in the form of radiation. I told you, everybody radiates. We lose heat in the form of radiation. Radiation is not the topic that we are studying right now. Right now, we are concentrating on conduction, so we need to concentrate on conduction. So I have a solid body. One end, let us say, is maintained at temperature T1. The temperature of this end remains constant. The other end is temperature T2. This also remains constant. Obviously, we can encounter cases where T1 and T2 also changes, or any one of those changes. There are questions, a lot of questions on this. We'll do one of those probably, and basically it's from SC Verma, so we'll try to solve that. Anyways, T1 and T2, we are talking about steady state. Now T1 is more than T2, as I have already done. T1 is more than T2, so heat will get transferred. Heat will get transferred and will flow like this, in the direction of the green arrow. The heat flows like this. Let us say delta Q amount of heat, delta Q1 amount of heat has started flowing from the end A. Let me call this end as end A. Let me call this end as end B. Delta Q1 amount of heat. The process of conduction has just started. I have just two different points. One is a temperature T1, other is temperature T2, and I've connected a metal rod between them, and I'm trying to steady the process of conduction. In the beginning, delta Q1 amount of heat, let us say, is getting transferred, is leaving the end A. What do you think? How much amount of heat will be reaching end B? Will it be the same amount? Will it be more than the amount that has left A, or will it be less than the amount that has left A? Tell me. Will it be more? Will it be less? Will it be equal to? The process of conduction has just started. No idea? Less. Yes, it has to be less. So let us call this as delta Q2. And this delta Q2 is less than delta Q1. Why? That is the next question. Why it is less? Why it should be less? Why whatever heat is leaving end A, why the same heat is not reaching end B? Why it is less? And the logical answer is, this has got nothing to do with physics. This is common sense. The logical answer would be, If I take any particular section of this, let me say this is a section of this, whatever heat is entering this section, whatever heat is entering this section, the same heat is not leaving this section because some amount of heat is getting absorbed in the section. This small section will be absorbing heat so that this also gets hotter. The small section will be absorbing heat. All these sections in between A and B will be absorbing some amount of heat, and therefore the heat leaving end A and the heat reaching end B will not be same. There will be a difference because some amount of heat is absorbed. Now let us say that I keep this temperature T1 and T2 constant. T1 and T2 does not change. We call them large reservoirs of temperature. For example, T2 may be connected to a refrigerator, which is keeping it at a constant temperature. The other, we have burned some fire and we are keeping that fire on and on, so that temperature T1, we call it large reservoirs. For a large reservoir, the temperature does not change so much. So T1 and T2 are maintained constant. Now, the process of conduction will keep on going. Now, there will be a time that comes. What will happen at that time? After some time, whatever heat is leaving section A, if I say delta Q amount of heat, this is after some time, it leaves section A. After some time, the same amount of heat will be reaching section B. Do we understand this scenario? Whatever heat leaves section A after some time, if the process continues, the same heat will be reaching point B. That means no heat is lost, no heat is absorbed, no heat is absorbed in the intervening section, no heat is absorbed. No heat is absorbed in between the sections. This state, when whatever heat leaves point A, the same amount of heat reaches point B, is known as, my dear friends, the steady state. And most of the questions that we are going to do will be based on this steady state. Whatever heat is leaving point A, the same amount of heat is leaving point B. Do we understand this? Can I have some reason that we understand this? So that is what I mean by steady state. Now, once I understand steady state, we'll try to note down some points about steady state. But before going on to those points, let us understand one more term which is known as temperature gradient, because we might be using this. We will be using this. Temperature gradient. Have you heard this term, temperature gradient? This is same as your velocity gradient or any gradient. Temperature gradient. Have you heard about this term, temperature gradient? What is temperature gradient? It's very simple. Let us say we have taken a section. Let me mark that section. I have taken a section here. Now, in between this section, there will be a difference of temperature between, I'll just draw this section in, this is the section that I have taken. I hope you understand this. This is the section that I have taken. In between this section, there will be a difference of temperature between the two ends. Let me call the difference of temperature between the two ends as dt. Or if I don't want to call dt, let me call it as d theta, because we are using theta for temperature. The difference in temperature between the two sections is d theta, and the width of this section is, let us say, dx. So basically what I mean to say is, for a difference or for a distance of dx, the temperature changes by d theta, The ratio of this d theta, I should not call it ratio, d theta by dx is known as the temperature gradient. D theta by dx would be known as the temperature gradient of this small section. Do we understand this? D theta by dx. So this is basically the change in the value of theta for a change in value of x. So tangent and all those straight lines and all those things come. If I draw a graph between what? If I draw a graph between x and theta, if I say this is the graph, this d theta by dx is the tangent of this graph. Do we understand this? It's very simple. This d theta by dx is the tangent of this graph. So tan of phi is your temperature gradient. Do we understand this? Okay. This is the temperature gradient. Similar to temperature gradient, we have velocity gradient in fluids. When you might have seen laminar flow of fluids, on the top, the velocity is v, on the bottom, velocity is 0. Velocity gradient is v minus 0 divided by the length, or velocity gradient, if I call it as velocity gradient, dv by dx is known as the velocity gradient. You remember this term, velocity gradient? That was in fluids. Same thing. Same thing. Or you might have heard about potential gradient in electric current. Potential gradient, change in potential divided by the distance. You might have heard this term in potentiometer. You might have heard this term in meter bridge or potentiometer. Potential gradient, same potential gradient. If instead of V, I call V as potential or potential difference, dV by dx becomes your potential gradient. Doesn't change anything. The concept remains same. Now, let us try to write the important points about this steady state, and we should not forget this point because based on these questions will come in your exam, and everything depends on whether you have understood these points on steady state or not. Point number one, what happens in steady state? Amount of heat entering any section will be equal to amount of heat exiting that section. Do we understand this? The other way of saying this is no heat is absorbed in any of the sections. No heat is absorbed in any of the sections. Now, what we are going to do is try to understand these things in different ways. No amount of heat is absorbed. Whatever heat is leaving, same heat reaches the other section, or I can say the rate of heat flow. Rate of heat is constant. Do we understand this? Rate of heat is constant, or I can say dq by dt is a constant. Do we understand this? Can I have some raised hand that will help me because I can't hear you? The rate of heat is constant. We understand this? Rate of heat flow. The rate at which heat is flowing is constant. That does not change. Now, again, temperature will fall from one end, that is A, to end B. So one end is a temperature A, one end is temperature T1, the other end is temperature T2, and the temperature will keep on falling or rising the way you see it from end A to end B. Different sections, if I take different sections would be at different temperatures that remain constant with time. Do we understand this? Different sections would be at different temperatures, and that different temperatures, they are different between the sections, but they will remain constant with time. Remember, temperature of two sections cannot become same, because if the temperature becomes same, heat stops to flow. It will keep on flowing only when there is temperature difference. If there is no temperature difference, heat does not flow. It is same as electric current. To make electric current flow, you need to have potential difference. If there is no potential difference, no heat flow. If there is no temperature difference, if there is no potential difference, there is no current flow. If there is no temperature difference, there is no heat flow. Do we understand this? Can I have some reason that we understand this? So if I go back to my different sections, and here, this section is at temperature T1. The temperature is T1 here. This section is at temperature T2. Now, if I take any section in between, let me call the temperature of this section as theta1. Let me call the temperature of this section as theta2, and so on. I make different sections from here to here. All these different sections that I have created, chota sections, they will have different temperatures, but those temperatures will remain constant. That means this theta1 will remain theta1, this theta2 will remain theta2, theta3 and so on will remain theta3, this T1 will remain T1, and this T2 will remain T2. The temperature of different sections are different. They cannot become same. If they become same, heat transfer stops, conduction stops, nothing happens. They must remain same but different from each other with time. Do we understand this? I hope you understand this. The other way of saying this thing is, we can write this: the temperature gradient d theta by dx remains constant. The temperature gradient d theta by dx remain constant. Right now I can call it as T1 minus T2 or T2 minus T1 divided by L, where L happens to be the length of the rod. Do we understand this? D theta by dx, the temperature gradient will be constant. You take any section, you find out the temperature gradient of that section, you find out the temperature gradient of that section, and that temperature gradient of that section will be constant, and that will be equal to T1 minus T2, higher temperature minus lower temperature, divided by the entire length L. Or I can say this in a different way. I have drawn the graph over here. I can say this in a different way, that the graph between theta and x would be a what? This will remain constant. This will remain constant. That means what? This will remain constant. That means what? The graph between theta and x would be a what? This would be a straight line graph, and that is what I have drawn here. This is exactly similar to what we have studied in fluids. The velocity gradient remains constant. Velocity gradually falls from one end to the other end. dV by dx is a constant. Similar thing you have studied in potentiometer. The potential gradient across the potentiometer across the wire of the potentiometer or the meter bridge remains constant. Can I have some raised hand that we understand this? So we are doing one thing, but we are relating other things with the same thing because they mean the same. Yes or no? No? Oh yes. Yes or no? No or yes? Yes or no? Okay. Then what we can, then I hope you have written this. Everyone is writing with me. Now we can formulate an equation that will give us how much heat has flown. If I say delta Q amount of heat has flown from end A to end B, remember I'm talking about steady state. Delta Q amount of heat is flown. It will be proportional to T1 minus T2, or instead of T1 minus T2, let me write as theta 1 minus theta 2, because I want to use the same term that we have started. It will be proportional to theta 1 minus theta 2. The more the temperature difference between the two ends, more heat will flow. It will be proportional to the area of cross section of this rod. The more motor, the more thick the rod is, more heat will flow. It is inversely proportional to the length of the rod. More the length, less is the conduction, because it will take more time. It will depend on the time delta t. How much time the heat has flown. If the heat has flown for a long time, more heat. Less time, less heat. It will also depend on the material of the body. I hope you understand this. Everyone understands this. So I can now formulate a simple formula. I can write it as delta Q will be equal to K. This K comes from the constant of the material. Do we understand this? It depends on the property of the material. I hope everyone is now aware how I write things. K A theta 1 minus theta 2 divided by L multiplied by dt. Do we understand this? Can I have some reason that we understand this, sir? Okay, now what I can do is I can just bring this dt time on the other side, and I can write the above equation in this form. Delta Q by delta T is equal to Ka by L multiplied by theta 1 minus theta 2. I hope you understand this. This becomes my basic equation for finding out the heat which has flown per unit time, or the rate of heat flow. And we all know now that this rate of heat flow is also known as heat current. Yes or no, my dear friends? So I'll call it as IH. I heat. IH d delta Q by delta T is known as IH. Now this is the form that we'll write it normally because it is a steady state, so we can write it that way. But sometimes your area of cross section may vary. You can have different questions where your area of the rod is getting varied. Your K is getting varied. So even if your temperature gradient is constant, K and A can vary. So I should also have a differential form of the equation which is meant for a very small cross section. What is the differential form of this equation? When things get varying, how do I find the heat current? What is the differential form of this equation? Same equation, differential form. Small form. I hope you have seen this form. Yes, bacha. What is the differential form of this equation? Any idea? No idea? Get idea. The differential form of this equation is very simple to understand, and it is very simply equal to dq by dt for a small section. dq is the small amount of heat that has flown. dt is the small time in which that heat is flown. dq by dt is k, the constant for that section. Do you know what this k is known as? Do you know what this k is known as? This k is known as the coefficient of thermal conductivity. I hope you all know this. This is known as the coefficient of thermal conductivity. You can find out its dimension and its units. I am not going to get into that. I hope you are good enough to understand this. Coefficient of thermal conductivity, K. So dq by dt is K, the coefficient of thermal conductivity of that section. It may be varying. Multiplied by A, area of the cross section. This area could be varying, into d theta by dx. Remember this. And we have a negative sign because you remember heat only flows from higher to lower, higher to lower, higher to lower. So if I'm going from A to B, the temperature will decrease. That is why this negative sign. This is the differential form of the equation which will be used if any of these things start to vary. Do we understand this? Can I have some reason that we understand this, sir? Yes, sir. No, sir. Better I go, sir. Better you go, sir. Yes, sir. No, sir. We understand this? No, 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 no. Both the forms, differential form and the normal form. Yes, sir. Yes, sir. I hope you have noted it, sir. That takes me, since I've used what? Since I've used what? Since I've used what? Since I've used what? Since I've used IH, thermal current, heat current, I must also try to write it in the form of current. Electric current flows because of difference in potentials. If there is potential difference, electric current flows. We all know this. Thermal current or heat current flows because of difference in temperature. So I can write this way: IH is equal to theta 1 minus theta 2. Difference in temperature divided by, if I can write it as RTH or R thermal. This now starts to look in the form where I is equal to delta V, change in potential or difference in potential, divided by R. Yes or no? Yes or no, my dear friends? This I here was electric current. This I here is thermal current. This delta V was difference in potential. It is now replaced by delta theta. This R. This R, gentlemen. I love this R. I will make it yellow. This R, gentlemen, has been replaced by thermal current. So everything has a resistance or opposition to flow of current. That is known as the electrical resistance. That same thing would have resistance to any flow, opposition of any flow. If heat is trying to flow in the form of conduction, it will also resist it. We call it thermal resistance. Do we understand this? Now we also know that this thermal resistance, RTH, is equal to how much, my dear friends? How much is this? I can just understand it. I can write it as L divided by Ka. Do we understand this? Yes or no? This is L divided by Ka, where K is known as the coefficient of thermal conductivity. Thermal conductivity. Thermal conductivity. Do you all understand this? Now, if I go back in the past, and I love going back in the past because past is always beautiful. The best part of your life is when you are young kids and you enjoy it. College part is your best part in life. The only memories I have is from my college life. There are no memories still left. Now, if I talk about resistance, I could have written resistance as rho L by A. I hope you remember this rho L by A. Now, if you look here closely, this L and A are same here. L and A. L and A are same here. L is the length, A is the area. Now, this gentleman that remains here, K, this K wala gentleman is coefficient of thermal conductivity. This is coefficient of thermal conductivity. This gentleman here is resistivity. Do we understand resistivity or electrical resistivity? Resistivity. But, you might have also heard a term conductivity, electrical conductivity of a wire. And the relation between conductivity and resistivity is very simple. It is very simple. You must recollect it that this, if sigma is your conductivity, it is 1 by rho. Do we remember this, my dear friends? Here this becomes your electrical conductivity. Yes or no? Do we remember this? This is electrical conductivity. Now, in light of this information that we already have, I can write this equation in this form. I can write it as L divided by sigma A, where this sigma gentleman is your electrical conductivity. And now if you compare these two equations are exactly same. Yes or no? L divided by Ka, thermal conductivity, L divided by sigma A, electrical conductivity. That means that we are dealing with the same thing. Yes or no? Do we understand this? We are dealing with the same thing here. There it was electrical conductivity, now it is known as thermal conductivity. There it was electrical resistance, now it is known as thermal resistance. There it was difference in potential, now it is difference in temperature. There it was electric current, now it is known as heat current. Do we understand this? Yes or no? I'll give you a minute to note it down. Well, I hope everyone has noted this down. Can I have some signals from your end that, sir, we have noted this down? This is the most important thing, because with this, we are going to solve all the questions that are ever going to come in this. Now, since we have understood that electric current and heat current are same, now we can understand the two types of connection. The first type of connection is, instead of resistance, we have rods in series. Rods in series. How will the rods in series look like? If I look here, it will look like one rod, number one, the other rod, number two, the other rod, number three. Now, instead of remembering them as rods, this end is maintained at temperature theta1, this end is maintained at temperature theta2. Instead of making them as rod, I'll just make them as resistance. It will take less time. This is resistance R1, this is resistance R2, and this is resistance R3. We all know that in this case, these three resistors can be removed and I can have the equivalent resistance R equivalent or R series will be equal to summation of Ri. Do we understand this? Do we understand this? In this case, the heat current IH, or I can say dq by dt, will be same. Dq by dt will be same, but the potential difference between the two rods. So if I call this temperature, I've called this as theta 1. If I call this as theta 2, if I call this as theta 3, if I call this as theta 4, theta 3 and theta 4 will be different. The potential difference or temperature difference would be different. So theta 3 minus or theta 1 minus theta 3 will be different. Theta 3 minus theta 4 will be different. And theta 4 minus theta 2 will be different depending on what is the resistance of these rods. Yes or no? Do we understand this? Can I have some raise hand from your end that we understand this? Now to give you a small thing, if I have this rod as rod, oops, if I have this rod as rod number 1 and I have this rod as rod number 2, this is maintained at temperature theta 1, this is maintained at temperature 2. This theta, this is the interface. Do you understand the interface? This is known as the interface. This is known as the interface. This theta is the temperature of the interface. Heat, I assume that is flowing like this, tongue, 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 and tongue. Whatever heat is leaving section A, which is delta Q by delta T, the same heat is entering this interface delta Q by delta T, and the same heat is leaving this section. Do we understand this? Simple diagram, very simple. Now I can write this equation in this fashion. I am assuming that this is greater than this is greater than this. So I can simply write it as, I can simply write the heat current is same equal to the heat current in the first section is theta 1 minus theta divided by resistance R1. I hope you understand this. Can I have some raise hands? That will be equal to theta minus theta 2 divided by R2. Can I have some raise hand on this one? This will be same as theta 1 minus theta 2 divided by R series or R equivalent, which is equal to R1 plus R2. Do we understand this, everyone? Now, the same thing could be done for electric current. So if I have done this, we have also done electric current. So congratulations, we are done electric current. This is all you need to know about electric current. Whatever questions you have done in electric current, same question could have been made in heat. I'll give you a minute to note this down, then we'll do the parallel connection as well. Okay, since you have done this, we'll just do the parallel connection and we will go ahead in our lives. So the second connection would be number 2, parallel connection. Parallel connection. And in this parallel connection, what will happen if I just draw it in terms of rods? Since you should be able to understand in terms of rod, this is rod number 1. This is a different rod made up of a different material. Rod number 2, they are put like this. The temperature of this end is theta 1. The temperature of this end is theta 2. Whatever heat is entering here, the same heat has to exit here. I hope you all understand this. I write it as delta Q by delta T. That is the heat leaving section 1. Delta Q by delta T. This is the heat entering the last section. But remember, the heat in this section would be different. In section number 1, I call this as section number 1. I call this as section number 2. In section 1, the heat is delta Q1 by delta T. I hope you understand this. In section 2, the heat is delta Q2 by delta T. We all know this, that delta Q by delta T, the total heat, shall be equal to delta Q1 by delta T plus delta Q2 by delta T. This is Q2 by delta T. I hope all of you understand this. Or I can write it like this. Theta 1 minus theta 2 divided by R equivalent or R effective will be equal to, theta 1 minus theta 2 divided by R1 plus theta 1 minus theta 2 divided by R2, or I can simply write it as 1 by R effective will be equal to 1 by R1 plus 1 by R2. That becomes the effective resistance of the circuit. Do you understand this, everyone? Well, I have already sent you the sheet. The sheet has certain questions. You can solve those questions on your own. Well done. Else in the next class, we will try to solve some questions on heat, on conduction, and we will try to wind up this chapter. This is it from my end. I shall meet you in the next class tomorrow. Till then, please keep on studying, and I hope you love this class. Take care and have a nice day.